So this one is a general notation for normally differential equation of first order and higher degree. A function of x variable, y variable, p variable. P stands for dy by dx equals to 0. Now, in the previous lecture, we discussed how to solve this kind of equation when it is solvable for p variable. In this video, we'll discuss how to find general solution of this kind of equation when it is solvable for y variable. Now, let us write this general notation as our equation number 1. Now, suppose if it is possible that we can solve it for y variable, now it means we can write equation number in terms of y equals to some function of x and y variable. Let us write it, give it a name, and that is this is equation number 2. The next step is we will differentiate equation number 2 with respect to x. So dy by dx, it will become p. This is equals to g. It will involve x variable, p variable, and derivative of p with respect to x. This is our equation number 3. So by differentiating equation number 2 with respect to x, we have eliminated the y variable. Now, out of equation 3, we select that factor which involve this first order, first degree differential equation with the p as dependent variable and x as independent variable, and we solve it for um, for p as dependent variables. Okay, so equation number 4 will be a first order, first degree equation in with the p as dependent variable. Solve it, and that way we'll get a function of say x, and we'll have arbitrary constant c. So our equation number 5, we'll eliminate p between equation number 2 and 5, or we can say that we will eliminate p between equation number 2 and 5. So p will be removed from equation number 2, and we will get y as a function of x variable, and it will involve arbitrary constant also. So that way we will get solution of the first order and higher degree equation as y equals to z x comma c. This will be our solution. So let us take an example to see how to implement these ideas. The first example is we have to solve this differential equation, and the differential equation is 2 of x plus e raised to the power 4 minus y equals to 0. Now this equation involved e raised to power 4, so this one is the fourth degree first order ordinary differential equation. We may try to solve this using the method. It will be difficult to solve this equation by factorizing this equation into linear factors of 2. So alternatively, we can see that this can be easily solved for p, right? So for solving it for variable y, we write it as y equals to, this becomes 2px plus p raised to the power 4 get. Let us give it name 2 original equation as equation number 1. So we are at step number 2, right? Next step is we have to uh, take derivative of equation 2 with respect to x. So dy by dx, this is equals to derivative of right hand terms, and right hand terms involves, we have two terms, 2px and e raised to the power 4 x squared. Now this can be further solved as derivative of 2 x plus derivative of e raised to the power 4 x squared. We will apply UV rule here. 2 comes outside, e as it is, x derivative with respect to x, it will be 1 plus second function x, and derivative of p with respect to x, it will be dp by dx. So bracket close. First, again, we will use UV rule here to find the derivative. So we have first of a function p raised to power 4 x square, derivative with respect to x, it will be 2x plus x squared. Now equals the power derivative with respect to x. We apply chain rule, so this will be 4 p cube and dt by d. Now we can write dy by dx as p. So equation is p equals to 2 of p plus 2x dt over dx plus 2x p raised to the power 4 plus 4x squared cube dt by dx. Now p can be adjusted with the 2p. So 2p minus p, it will become p plus 2x dp by dx, and this one is plus 2x e raised to power 4 plus 4x squared p cube dp by dx. This is equals to 0. So we have brought this p on the left hand side to right hand side. Okay. So we have cleared the clutter, and we have p plus 2x dp over dx. From the last two terms, we can take out common 2x and p cube. So inside the bracket, we have p plus 2x dp over dx. And we also have first two terms as p plus 2x dp by dx. Now, out of these two terms, we can take out p plus 2x dp over dx as common. And inside in the other factor is we have 1 plus 2x p cube, and this is equal to 0. Now, as we need the general solution of the given equation, we will consider the first factor and equate it to 0, and solve it for p in terms of x. The second factor does not involve dp over dx, and it will give us a singular solution. So right now we are interested only in the general solution. So we are taking out this considering this factor. A factor is 2 plus dx dp over dx, and we equate it equals to 0. This one is a first order and first degree ordinary differential equation with p as dependent variable and x as independent variable, and this is separable form. Okay, so we further simplify it. We can write it as p equals to minus 2x dp over dx. Okay, and now bringing it, writing it like 1 over p dp. P we have brought on right hand side, right? So dp over p, and this is equals to, we have minus 1 over 2 dx over x. So dp over p, dx goes here, dx over minus 2x, right? So this is a pure separable form. We integrate it. Integration 1 over p dp is equals to minus 1 over 2 integration of 1 over x dx, and plus arbitrary constant of integration. Integration 1 over p dp is log p minus half. Integration of 1 over x with respect to x is log x, and we know that if all the terms in an we know that when all the terms involve logarithmic function, we write arbitrary constant in terms of logarithmic function also. So this is log c. V is log p is equal to, we can write the first term as log x raised to the power minus 1 over 2 using the property of log, plus log c, And again, using the property log, we can write it as log of c x raised to the power minus of, and this is value of log p. Taking anti-log both sides, we get p equals to c x raised to the power minus half. So this is the solution of this first order and first degree equation in p and x variable. So the general solution of given equation 1 will be obtained by eliminating p variable from equation number 2 and equation number 3. So we simply put p value into equation number 2. So we get y equals to 2. In place of p, we will write c x raised to the power minus half into x, and plus p4 stand for c x raised to the power minus half whole power 4 multiplied by x square. And after simplifying, we get y equals to 2c x raised to power 1 minus half, this is x raised to the power 1 over 2, and this one is plus c raised to the power 4, x raised power minus 1 by 2 whole powers 4, it will be x raised power minus 2, and x raised power minus 2 into x raised power 2, it will be x raised power 0, and x raised power 0 is 1. So finally we get the solution of the equation, the originally given equation, as we have this equation solution as y equals to uh, 2c x raised to the power 1 over 2 plus c raised to the power 4. Let's take one more example. In this example, we have to solve this equation, and the equation is p cube plus e is equals to e raised to the power y. Okay, now because of this pq factor, this is first order in the higher degree ordinary differential equation, and it involves y variable and p variable only. So it's possible to solve it for y. So we take logarithm both sides. So this becomes natural log of p cube plus p, and this is equal to y. So this equation is solvable for y. Let us give name equation number 1 to the originally given equation, and after simplification we write it as y equals to log p cube plus p. Let us write it as equation number 2. Now before we take derivative of this equation with respect to, let us first simplify it further using the property of log. So we can write it as log p is taken out as common, and this becomes p square plus 1, and we have y equals to, using the property of log m into n is log m plus log n. So this will be log p plus log p square plus 1, and this is our equation number 3. Right. Now we use the properties of log because it will make things easier for us later when we integrate the differential equation, right? Now next we take a differentiation of this with respect to x, so we get dy by dx. This is a derivative of log p plus log p square plus 1. Now this one is equals to derivative of log p. Will apply chain rule here. Log p, derivative of log p is 1 over p, and then derivative of p with respect to x, this will be dp over dx. Plus similarly here, derivative of log p square plus 1 with respect to x, chain rule. uh, Derivative of log, this will be 1 over p square plus 1, and then derivative of p square plus 1, p square, again chain rule, p square for 2p dp over dx, and plus derivative of constant 1 is 0. So dy by dx, we write it as p. This is equal to 1 over p dp over dx, plus this one is 2p over p square plus 1 dp over dx. By dx factor is common, so we can write it as dp over dx over p plus 2p over p square plus 1. Now, this is a separable equation because we can take all the function involving p with the dp, and this will be converted into. So now equation is p equals to dp over dx 1 over p plus 2p over p square plus 1. Okay, so we divide throughout by p, our equation will become 1 is equals to dividing by p. So this will become 1 dividing by p. This will be 1 over p square. This one is plus 2 over p square plus 1 dp over dx. Right? And now we convert it into a separable equation. We take a dx differential on the left hand side. So this becomes dx is equals to 1 over p square plus 2 over p square plus 1 dp. This is our first order and first degree separable equation with in p variable and x variable. Now we used log property earlier, and now we are reaping the benefits over here because we can easily differentiate, integrate the function inside the bracket with respect to p. So this is separable equation. Now we integrate it. Integration dx is equals to integration p raised to the power minus 2 dp plus this one is okay 2 integration 1 over p square plus 1 dp plus arbitrary constant c. On the left hand side becomes this is equals to integration of p raised power minus 2. This is p raised power minus 2 plus 1 over minus 2 plus 1 plus 2 integration of 1 over p square plus 1. This is tan inverse p and plus arbitrary constant c, and we simplify it. X equals to this one is minus 1 over p minus 2 plus 1 is minus 1 1 over p plus 2 or 10 inverse p plus c. We give this equation name as equation number 4. Now we know that we get the solution of the higher degree equation by eliminating p from equation number 2 and equation number 4. But in this case, it becomes very difficult to eliminate p from these two equations. So we'll write the final answer as that the solution of the differential equation is obtained by eliminating p from equation number 2 and 4. The general solution of given differential equation is obtained by eliminating p from equation number 2 and equation number 4. So in this video, we learn how to solve a ordinary differential equation of first order and higher degree, which is solvable for y variable. Thank you.